Today, math learners, we will continue talking on the logarithmic functions. So in this video, we will be focusing on the logarithmic function and its basic concepts. Let us try to recall on the common logarithm and natural logarithm. When we say common logarithm, it is a logarithm with base 10. This common logarithm is written without a base. For example, the logarithm of 100. This usually means that the base of this form is 10. So meaning, it can be written in this form, the logarithm of 100 to the base 10. On a calculator, it is the log key. It is how many times we need to use 10 in a multiplication to get our desired number, and it is read as the common logarithm of 100 or the logarithm of 100 is equal to 2. For natural logarithm, it is a logarithm with base e. So it is another base that is often used. That stands for Euler's number, which is about 2.7182818228. Please take note that for every log or the logarithm of x to the base e, it is equal to the natural logarithm of x or ln of x. So for every y is equal to ln of x, okay, it can be written to its exponential form, which is x is equal to e raised to y. For example, if we have ln of 7.389, it can be written into this form, the logarithm of 7.389 to the base e. So if we are going to get its value, we can press the ln key found in your calculator and press the number 7.389, and it's approximately equal to 2. Or if we have e raised to 2, it is approximately equal to 7.3890. So this time, we will be talking on the anti-logarithm. The logarithm is a word made up by Scottish mathematician John Napier. The base e logarithms are called natural logarithms or sometimes called Napierian logarithm in honor of its inventor. John Napier also introduced anti-logarithm. The study was left to Leonhard Euler. If the logarithm of a number is given and the number to be found, this number to be found is called the anti-logarithm of a given number. The anti-logarithm of a number n, or antilog of n, is equal to the number n. In symbols, the anti-logarithm of logarithm of n is equal to n, or it can be read as the antilog of log of n is equal to n. For example, we need to find the value of each anti-logarithm. So this is the given, and here are the solutions. First, we are going to equate the given anti-logarithm with n, and then use the symmetric property of equality so that the known variable n should be written at the left side of the equation, and the outcome will be like this. To find the value of n, use the scientific calculator and press the keys shift, log, and the given number equals, and the answer is 2.5, and n is equal to 2.5. Let's recall this process, that if we are going to get the value of the logarithm of 2.5, its result is 0.3979400087. Using your calculator, we can press the key log, this number, equals, and this is our answer. Therefore, if we have this logarithm of n is equal to x, it is equal to the antilogarithm of x equals n. If we have the logarithm of 2.5 equals 0.3979400087, it is equal to the antilogarithm of 0.3979400087 equals 2.5. To check, okay, we are going to use the first step in our solution. Just copy, and then this antilogarithm, or the given antilogarithm, can be written into this form, and copy equals 2.5. And if we are going to get the result of this number, then it is 2.5. Therefore, this 2.5 is considered as our solution to make our equation correct. So this is the given, and here are the solutions. First, again, we are going to equate the given antilogarithm with n. Use the symmetric property of equality so that the known variable n should be written at the left side of the equation, and the outcome will be like this. To find the value of n, use the scientific calculator and press the keys Shift, Log, and the given number equals, and the answer is 4, and n is equal to 4. So let's recall this process, that if you are going to get the value of the logarithm 4, its result is 0.6020599913. Using your calculator, we can press the log, and then the number 4 equals this number. So therefore, if the logarithm of n is equal to x, okay, it is simply equal to antilogarithm of x is equal to n, or the logarithm of 4 is equal to 0.6020599913. It is equal to the antilogarithm of 0.6020599913 equals 4. To check if the equation is correct, we will write the given antilogarithm and equate it with the value of n, which is 4. This given antilogarithm can be written into this exponential form, then copy equals 4. The result of exponential form of the given antilogarithm is 4. Then copy equals 4. Therefore, the value of n, which is 4, is the solution to make our equation a true mathematical statement. Since we are asked to find the principal 16th root of 36, okay, let us have to transform this statement into its symbol. So its symbol will become 16th root of 36. Now, here are the solutions. So we are going to equate this given to n. After that, we will transform this radical expression into its exponential form, and n is equal to 36 raised to 1 over 16. What makes it 36 raised to 1 over 16? Because according to the definition of our radical expression, that for every nth root of a raised to m, it is equal to a raised to m, which is our exponent of our radicand a over n, which is the value of our index. So the exponential form of this 16th root of 36 is 36 raised to 1, which is the exponent of 36, over 16, which is the value of our index in our radical form. So that is why we have this. Next, we are going to take the common logarithm of both sides of the equation, and it will become logarithm of n is equal to the logarithm of 36 raised to 1 over 16. Since 1 over 16 is considered as our exponent of this logarithmic form, we will be using the power rule of the logarithm. So our equation will become the logarithm of n is equal to 1 over 16 times the logarithm of 36. Now, get the value of the logarithm of 36 using your calculator. So press the key log and 36, and then the answer will become 1.556302501. Next, you're going to simplify this result by multiplying this result to 1 over 16, and the answer will become logarithm of n is equal to 0.0972689063. Now, since we are looking for the value of n, we will be using the concept of the antilogarithm. According to the concept of the antilogarithm, that for every logarithm of n, it is equal to x. We can consider this concept antilogarithm x is equal to n, or n is equal to antilogarithm of x. So therefore, this equation will become n is equal to the antilogarithm of 0.0972689063, and get the value of this antilogarithm, and using your calculator, and it will become n is equal to 1.251033405. So to check, so we are going to write the given and equate it with the value of n, which is 1.25 or 1.251033405, and then use your calculator. Press shift this symbol, and then the symbol that may appear in your calculator will be this one. After that, you input 16 and 36, and then press equal sign, and the answer would become 1.251033405, which is the value of n as the principal 16th root of 36. So this time we will be proceeding to the change of base theorem. According to the change of base theorem, that if b and x are positive real numbers, b is not equal to 1, then its symbol would be the logarithm of x to the base b equals the logarithm of x over the logarithm of b. So if we have the logarithm of 25 to the base 5, it is equal to the logarithm of 25 over the logarithm of 5. If we have the logarithm of 36 to the base 6, it is equal to the logarithm of 36 over the logarithm of 6. So we are asked to apply the change of base theorem to evaluate the logarithm. Here, this is our given, and here are the solutions. First is to write the given and equate it to the logarithm of 3 over the logarithm of 2. Why we have this equivalent value? Because according to the change of base theorem, that for every logarithm of x to the base b, it is equal to the logarithm of x over the logarithm of b. So we have this equivalent value. Now, get the equivalent value of the logarithm of 3 using your calculator. So we have 0.4771212547 over, get the value of our logarithm of 2 using your calculator as well. So we have 0.3010299957. Simplify them further using the division process, and the equivalent value of the logarithm of 3 to the base 2 is equal to 1.584965. Okay, to check, okay, you have to copy the given and equate it to its equivalent value, and transform this logarithmic form into this exponential form. And the value of 2 raised to 1.584965 is equal to this 2.999999, and it will become 3. Copy equals 3. So therefore, this 1.584965 is the equivalent value of our logarithm of 3 to the base 2. Another example in applying the change of base theorem. This is our given, and here are the solutions. First is to write the given and equate it to the logarithm of 8 over the logarithm of 3. Why we have this equivalent value? Again, because of the change of base theorem, that for every logarithm of x to the base b, it is equal to the logarithm of x over the logarithm of b. Next, get the equivalent value of the logarithm of 8 using your calculator, and it will become 0.903089987 over, get the value of the logarithm of 3 using your calculator, and it will become 0.4771212547, and the logarithm of 8 to the base 3 is equal to 1.89278961. To check, so write the given and its equivalent value, which is 1.89278961. After that, you're going to transform this logarithmic form into exponential form, and it would become 3 raised to 1.89278961 equals 8. Now, simplify this expression, and it will become 8.00003, or simply 8 equals 8, meaning to say that 1.89278961 is the equivalent value of the logarithm of 8 to the base 3. Here is another example, but this time we are going to solve for the value of x given the exponential equation, wherein change of base theorem is also applied. So this is the given, and here are the solutions. First, we are going to write the given, and then after that, this given should be transformed into the logarithmic form. So we have the logarithm of 25 to the base 3 is equal to 2x minus 1. Now we are going to use the symmetric property of equality so that the variable x will be placed at the left side of the equation. So we have 2x minus 1 equals the logarithm of 25 to the base 3. Now we are going to use the change of base theorem so that the logarithm of 25 to the base 3 will become the logarithm of 25 over the logarithm of 3. After that, we are going to get the value of the logarithm of 25. So we have 1.3979400009 using your calculator, and get also the value of the logarithm of 3 using your calculator. So we have 0.47712125447. So simplify them further using the division process, and the equation will become 2x minus 1 is equal to 2.9299470042. After that, transpose negative 1 to the other side of the equation, and it will become 2x is equal to 2.9299470042 plus 1, and get its sum, and it will become 3.9299470042. After that, we are going to divide both sides of the equation by 2 so that x will be isolated, and our value of x is equal to 1.964973521. Now to check, in order for this value of x is the solution to make our equation a true mathematical statement. So we will be copying the given first and substitute the value of x, which is 1.964973521, and simplify this left side of the equation by multiplying first 2 and the value of x. After that, we have 3 raised to 3.9299470042 minus 1 equals 25, and simplify them further, and it will become 3 raised to 2.9299470042, and get the result of 3 raised to 2.9299470042, and the answer will become 25.000002 equals 25, or simply 25 is equal to 25. That makes our equation a true mathematical statement. So this time, we will be solving the natural logarithm. The natural logarithm of a number n is denoted by its definition, ln of n. So if we have ln of n is equal to x, it implies that n is equal to e raised to x, because in natural logarithm, the base is considered as e, the exponent is x, and its result is number n. If we have ln of n is equal to x, it implies that ln of e raised to x is equal to x, because we just simply substitute the number n to its equivalent value, which is e raised to x. If we have n is equal to e raised to x, we can take the common logarithm of this expression, and it will become the logarithm of n is equal to the logarithm of e raised to x, or it can be written as the logarithm of n is equal to x times the logarithm of e. Thus, the logarithm n is equal to x times the logarithm of e. So we are going to substitute x here with the ln of n, since this is the definition of our natural logarithm. So our equation will become the logarithm of n is equal to the natural logarithm of n times the logarithm of e. Now, e here has the value of 2.718281828. So our equation will become the logarithm of n is equal to the ln of n times 0.43429444819, and our equation will become the logarithm of n is equal equal to 0.4343 times ln of n, or ln of n is equal to the logarithm of n over 0.4343. The factor 0.4343 is called the modulus of common logarithms. Modulus is a factor by which the logarithm to a given base of a number must be multiplied to obtain the logarithm of the same number. Please take note on these properties of natural logarithms. Number 1, if we have e raised to ln of x, it is equal to x. And for the number 2 property of natural logarithm, we have ln of e raised to x is equal to x. For example, if we have e raised to ln of 10, its value is equal to 10 because we apply the first property of natural logarithm. If we have ln of e raised to x plus 1, it is equal to x plus 1 because we apply the second property of the natural logarithm. For example number 1, if we have this given ln of 2, so we are asked to use the relation of ln of n is equal to the logarithm of n over 0.4343 to evaluate this natural logarithm. So our solutions are, first is to write the given and equate it to the logarithm of 2 over 0.4343. Next, get the value of the logarithm of 2, which is 0.3010, using your calculator, over 0.4343, and the value or the approximate value of the natural logarithm of 2 is 0.6931. To check, just write first the given and its approximate value, which is 0.6931, and then use your calculator, press the key ln, and then 2 equals, and the answer would be 0.6931 for 71806. For example number 2, the given is ln of 22.5. So we are asked to use the relation of ln of n is equal to the logarithm of n over 0.4343. Now, here are the solutions. First is to write the given and equate it to the logarithm of 22.5 over 0.4343. Next, we are going to get the value of the logarithm of 22.5 using your calculator, and it will be 1.3522 over 0.4343. Next is to simplify using the division process, and the approximate value of the ln of 22.5 is 3.1135. Now, to check, we are going to write the given, which is the ln of 22.5, and its approximate value, which is 3.1135. So press ln and then 22.5 equals, and the answer would be 0.6931471806 in your calculator. So this time we are asked to solve for the value of x given the natural logarithmic equation, which is ln of x is equal to 1 plus 2 ln of 2. So here are the solutions. First is to copy the equation, and after that we are going to transpose 2 ln of 2 to the other side of the equation, and it will become ln of x minus 2 ln of 2 is equal to 1. Next is to use the power rule of the logarithm. So our equation becomes ln of x minus ln of 2 raised to 2 is equal to 1. So next is to simplify further. Our equation becomes ln of x minus ln of 4 is equal to 1. After that, since our equation here shows the difference of two logarithms, so we will be using the quotient rule. So our equation becomes ln of x over 4 equals 1. After that, we are going to make this logarithmic form into exponential form. So our base is e, our exponent is 1, and our result of this exponential form is x over 4. So after that, we are going to multiply both sides of the equation by 4 since we are looking for the value of x here. So x is equal to 4e. Next is, since e has the value of 2.7183, so we are going to multiply it by 4 and x becomes 10.8732. Now, to check our solution, so we are going to use the given. So we have ln of x is equal to 1 plus 2 times ln of 2. Next is substitute the value of x, which is 10.8732, and our equation becomes ln of 10.8732 equals 1 plus 2. And then the value of ln of 2 using your calculator is 0.6931 or 71806. Now simplify them further. So the value of ln of 10.8732 is 2.3863 equals 1 plus the answer of 2 times 0.6931471806 is 1.38629431, and then get the sum of this expression in the right side of our equation, and it will become 2.38629431, or simply the equation becomes 2.3863 equals 2.3863. Please do not forget that the approximated value of a is 2.7183. Solve for the value of x given the natural logarithmic equation, which is e raised to ln of 2x plus 3 equals 17. Now here are the solutions. So first, you are going to copy the equation and then take the natural logarithm of both sides of the equations, and the equation becomes ln of e raised to ln of 2x plus 3 equals ln of 17. Now, we have this property of natural logarithm that for every ln of e raised to x, it is equal to x. So if we have ln of e raised to ln times 2x plus 3, it is equal to ln of 2x plus 3. So our equation becomes ln of 2x plus 3 equals ln of 17. Now, apply the property of equality of the logarithm because the bases of the two logarithms here are the same, which is e. So the equation becomes 2x plus 3 equals 17. After that, we are going to transpose 3 to the other side of the equation, and it will become 2x is equal to 17 minus 3. 17 minus 3, the answer is 14. Now, in order for us to get the value of x, so we have to divide both sides of the equation by 2, and x is equal to 7. Now, in order for us to check our solution, we need to copy the given logarithmic equation, which is e raised to ln of 2x plus 3 equals 17. After that, we are going to substitute the value of x, which is 7. So our equation becomes e raised to ln of 2 times 7 plus 3 equals 17. So simplify first 2 times 7 and the answer would be 14. 14 plus 3, the answer would be 17. Now, we have this indication about for every e raised to ln of x is equal to x, which is the first property of the natural logarithm. So if we have e raised to ln of 17, then it is equal to 17. So meaning to say 17 is equal to 17. That makes our equation a correct mathematical statement, a true mathematical statement. So this time, we will be considering the domain, range, zeros, intercepts, and asymptotes, as we will be dealing the graph of these logarithms. To find the domain and range of the logarithmic function, we have to consider first the given function, which is f of x is equal to the logarithm of x plus 2 to the base 2. Here are the solutions. First is to copy the given and then change f of x into y. Express this logarithmic form into exponential form and it will become 2 raised to y is equal to x plus 2. After that, use x plus 2 is greater than 0 to make the function defined. Please take note that use the inequality symbol greater than always, as you will get the domain of the logarithmic function. Next, solve for x, and x is greater than negative 2. Therefore, the domain is the set of all x values such that x is greater than negative 2. So, the graph at the right uses x is greater than negative 2. As you can see in the illustration, that the values of x are bound to the right of the graph from the broken line, which is considered as the vertical asymptote. So that's why the domain is the set of x values such that x is greater than negative 2. To find the range, as shown in the graph, y values are all real because graph can be extended upward and downwards. So y is equal to positive infinite number and negative infinite number. Therefore, the range is the set of y values such that y is the element of all real numbers. To find the vertical and horizontal asymptotes, we have to consider the given, which is f of x is equal to the logarithm of x plus 2 to the base 2. Now, here are the solutions to find the vertical asymptote. First is to copy the given. Next, change f of x into y. And then, express this logarithmic form into exponential form. So, the equation becomes 2 raised to y is equal to x plus 2. Next, equate x plus 2 to 0 and solve for x. And x is equal to negative 2. Therefore, the vertical asymptote is equal to negative 2. In our illustration, the broken line is considered as the vertical asymptotes. This line prohibits the graph of the given function to touch or cross it. So this time, we will be finding the horizontal asymptote. So first, we are going to equate x plus 2 to 0. As you substitute x with values having an interval of negative 2 to the positive infinite number, the values of y become larger and larger, or the output, which is f of x, will lead us to positive infinite number. So, therefore, no horizontal asymptote for this given function. So we are going to find the 0 or x-intercept and y-intercept of the logarithmic function. So consider this given function, which is the logarithm of x plus 2 to the base 2. So here are the solutions. Let y is equal to 0 and solve for x. So first, we are going to copy the given and then change f of x into y. And then substitute y with 0, and the equation becomes 0 is equal to the logarithm of x plus 2 to the base 2. After which, we are going to use the symmetric property of equality. That is why this is the face of our equation. Now, we are going to make this one into exponential form, and it will become 2 raised to 0 is equal to x plus 2. 2 raised to 0 is equal to 1, and then copy equals x plus 2. And then after that, you're going to transpose 2 to the other side of the equation so that x will be isolated, and it will become x is equal to negative 1. So this is our 0 and our x-intercept, and the coordinate point of our zeros or x-intercept is negative 1 and 0. So if we are going to look into the illustration, so our point lies on the x-axis, which is called as x-intercept, which is equal to negative 1. To find the y-intercept, here are the solutions. Let x is equal to 0 and solve for y. F of x is equal to the logarithm of x plus 2 to the base 2. So we have to copy the given. After which, we are going to substitute the value of x, which is 0. So y is equal to the logarithm of 0 plus 2 to the base 2. So simplify, and we have y is equal to the logarithm of 2 to the base 2. And y is equal to 1, because this is the property of the logarithm, that for every log of 2 to the base 2, it is equal to 1. So the y-intercept is 1 at 0, 1. So if we are going to look for the y-intercept in our illustration, so this is our graph of the logarithmic function with the x and y intercept. Thank you for listening, math learners. See you next time.